Hi everyone, I'm Farouk and today I'm presenting my work with my colleague Moin Khajanejad, accepted as a full paper to NetSciX 2022 named Hunting for Dual Target Set on a Class of Hierarchical Networks. Well, we all know here that complex networks have proved to be an exceedingly powerful and efficacious tool for describing a wide range of systems in nature and society. Thereafter, random search processes as an effective and informative way of exploring these networks have also attracted considerable attention towards them. In this work, we study the problem of partial cover time in a dual target search when performing a random walk on a 1-2 flower network. And for the first time, we derive an exact expression for the partial cover time of a random searcher on such a network to hunt both targets of interest. Now, we first start by a brief introduction of the main problem of partial cover time. This graph here shows an example of multi-object search on a yeast network. The expected time needed to find 6 distinct nodes, which are colored in green here, for a walker starting from the red source node with no prior knowledge of target distribution is defined as the mean partial cover time. Despite the long-lasting trend to solve this problem, the studies in the field are still in the early stages and not much effort has been made for finding a precise solution for it. The wide and common requirements for the simultaneous search for multiple targets in many fields such as chemistry, biology, and social interactions is what motivated us to study a dual target search under the scope of the partial cover time problem. As a general overview of the dual target search problem, on a typical network such as the one seen here, a random walker starts from node S and explores the network until meeting both targets of interest labeled T1 and T2 here. Now, to be able to characterize this type of search on a network, we use a partial cover time that can quantify the required time for a random walker to hit several different targets. Here, despite most recent efforts which study random walks and covering problems on complex networks mainly focusing on a single target case or estimating the full cover time of the entire network, we're trying to study multi-target search on complex systems. We specifically focus on the problem of hunting a target set containing 2 members on a class of UV flowers or pseudo-fractal scale-free web networks. As an example of hierarchical networks. Several key characteristics of complex networks can be modeled using these recursive, finitely articulated models. At the same time, these models can be precisely analyzed, giving us important insights into the nature of complex networks in everyday life. You can see a number of sample networks from this category here, and for this specific study, we will choose the 1-2 flowers. However, our proposed method can easily be applied to more general topologies of hierarchical lattices like other UV nets, and also the structures exhibiting a self-similar construction. These networks are built using an iterative method. Here we will see the evolution process of a 1-2 flower showing the first 3 generations. For all t greater than 1, the new generation or g of t is obtained from g of t minus 1 by attaching a new node to both ends of each edge. So at each time step ti, the number of newly added nodes is 3 to the power of ti, and the total number of nodes will then equal to 3 to the power of t plus 1 plus 3 divided by 2. So all nodes existing at iteration t or generation t equals to ti belong to levels 0 to ti. For example, looking at the right-hand side plot here, all purple nodes at generation 2 belong to level number 2 because they were only generated at the start of generation 2, when the blue nodes are from level 1 and yellow nodes belong to level 0 of generation 2. This class of networks exhibits some intriguing characteristics of real-life networks existing in nature. For example, the degrees of nodes obeys the power law distribution with the approximate exponent of 2.585, and also the average clustering coefficient tends to 0.8 when the network order is large enough, and the average path length increases logarithmically with the size of the network. Therefore, we can actually conclude that the 1-2 flowers express a small world behavior. Now, to come back to the problem of partial cover time we introduced earlier, we will avoid going into much mathematical detail here of our proposed framework, but if you're interested, please refer to our full paper, which will be soon published in the Proceedings of NetSciX 2022. Now, very briefly, consider a random searcher on a network who jumps from the current node I to one of its ki neighbors, for example, node j, at each time step, and this jump happens with transition probability, which is defined as pij, and this equals to 1 over ki. For the calculations without loss of generality, we assume that the two targets are located at distinct nodes 1 and 2. Here it's appealing to us to compute the partial cover time from node I to nodes 1 and 2, which alternatively means how long it takes for the searcher to reach both target nodes for the first time starting from node I. Here, T12 is the mean first passage time, or MFPT, from node 1 to node 2. Now, using matrix calculations and exploiting the fundamental matrix for the corresponding Markov process, eventually this relation reduces to the simpler form, as you can see here. Next, by employing a method based on probability generating functions, we try to derive an exact expression for the partial cover time for a two-target search in a 1-2 flower. Firstly, we bring a brief description of the probability generating functions. Let x be a discrete random variable which takes only non-negative integers like 0, 1, and etc. Now, by the definition, the probability generating function of x is the equation you can see here, where p is the probability mass function of x. Corresponding to different choices for an absorbing domain, here we particularly focus on nodes of levels 0 and 1, which are nodes with the largest and the second largest degrees. And again, without loss of generality, we suppose that these nodes are called A and F. We now derive an explicit expression of the first passage probability and mean first passage time for A and F separately, and then we will obtain the exact value of partial cover time later. For every generation of the network and each arbitrary starting node from generation T and level K of that generation, called Ck, we can compute the mean first passage time to nodes A and F. Employing the introduced probability generating function, the variable x would now correspond to the first passage time between source node Ck and each of target nodes A and F, and p of x will give us the probability of this first passage time. Eventually, our question translates to computing the expected value of x here, which will be obtained from this equation. Utilizing this equation, we derive the exact expression for this expected value in different cases where the source node C from generation T and level K is chosen from different subunits of the iteratively constructed network, which gives 3 different cases in a 1-2 flower. For details about these cases and subunits in the network, please refer to our full manuscript. Eventually, the average mean first passage time over all the starting nodes of level K to both nodes A and F can be captured analytically. Now it's time to reach our ultimate goal in this paper by following the previously proposed steps. We choose the source node C from level K belonging to a certain subunit. Then we have the following calculations for mean first passage time from Ck to A, mean passage time from Ck to F, and also mean passage time from A to F or vice versa. and eventually combining all these results and inserting in the general equation for partial cover time in the dual target search, which we talked about earlier, for any arbitrary source node from level k and any two arbitrary target nodes from level 0 or 1, we get the exact expression as you can see here. I should also note once again that these analytical calculations have been performed for all cases of source nodes chosen from different network subunits, and all the corresponding results and exact expressions can be found in the manuscript. Now, to conclude, we saw that in this work, for the first time, we can capture an expression to explicitly compute the partial cover time of the random walker until reaching both target nodes. This is in contrary to most previous efforts, which only focus on cover time calculation or more straightforward single target problems. The introduced formula for calculating this quantity outranks previous works in the sense that it can be conveniently applied to general types of networks, and our achievements in this work can be exploited as a pivotal method to solve the problem of partial cover time in general networks, and also establish the groundwork for future investigation in problems with a target set which includes an arbitrary number of nodes. Thank you very much for your attention, and please feel free to ask your questions in the conference session or via email.